Can we have Dr. Dibyendu Chatterjee, ICAR National Rice Research Institute, Cuttack?
Respected Chairman of the session, Co-Chair, Rapporteur and all other dignitaries. The topic I am going to present is enhancing phosphorus ability through nanoclay polymer composites impregnated with phosphorus and low molecular weight organic acids, and I am Dibyendu Chatterjee, Senior Scientist, Soil Science Division. Actually, phosphorus is such an element that it is having complex reactions in the soil, and because of that it is many times inaccessible to the plant. Now, the low molecular organic acid, we have our previous work that we have seen that it can increase the concentration of the phosphorus in the soil solution, and because of that we thought we can start a work where we can synthesize a polymer, nanoclay polymer composites, in which we can put both the phosphorus and the organic acid to have a composite which can help to giving phosphorus in a better way than the conventional way. So nanoclay polymer composites is the material consisting of nanoclay particles which is dispersed within the polymer matrix. Mostly we are utilizing polyacrylate polymers, so in the polyacrylate polymers it is dispersed. And the purpose of using this clay is to give mechanical strength, thermal stability and barrier properties. Now this is a diagram where we try to show the NCBC. We have synthesized the acrylic acid and acrylonitrile are co-polymerized in presence of nanoclay. We are using kaolin here, and with ammonium persulfate as the radical initiator and N,N-methylene bisacrylamide as the cross linker. And after that we dry it, and after drying we grind it and sieve it. So this is the conventional way, and our hypothesis, already I told, we want that it should improve the availability of both fertilizer phosphorus and the native phosphorus in the acid soil. And we observed that there is a research gap because very limited work is done on this topic. Now we have briefly two objectives to characterize these composites for water absorbency and feed release, and second to identify these smart delivery systems specifically for the upland rice. And while doing it, we have three sources of low molecular organic acid: citric, malic and tartaric acid, and three phosphorus sources, that is diammonium phosphate, DAP, SSP and rock phosphate. We are making 9 combinations, and the 9 combinations we have a challenge because the solubility of DAP is very high, whereas SSP solubility is moderately soluble, and the rock phosphate is water insoluble. So we have a different kind of solubility. So we thought of make one uniform method of synthesis, because mostly the low molecular acids and the phosphorus we used to dissolve in the water, and then we allow it to go inside the polymer matrix. But here since we have 3 different type of solubility, so we thought of making a new process. So here it is a synthesis of the NCBC, where acrylic acid and acrylamide was dissolved in water and then neutralized. Then after that we rotated in a magnetic stirrer, then kaolin was added, and then N,N-methylene bisacrylamide was added to it, and then it was mixed at the room temperature. Then we raised the temperature, and the radical initiator, I told that ammonium persulfate was added, and this polymerization starts. And here what happened, in between 3 and 4 steps we did this modification, and we add this polymer, the phosphorus source and the low molecular weight organic acid. So these are the different variants we have prepared. And first we after synthesis we did the characterization of the product, and here first we check it for maximum water absorbency, and we have seen that per gram of our material can absorb around 83 to 88 gram of water. So water absorbency is quite high. And we check the pattern of pre-release, because DAP was completely soluble in water. When we check that that it giving, if we make even after adding step 3, if we are making the product and we are using the conventional product, if we compare both, we have seen that both have a similar pattern and quantity of release. So we decide that let us go with the method which is direct addition of the material into the process. And what it will happen, if we do like that, then it will save time and also energy, because if you dry again reabsorb again dry, so some kind of heat energy is required, so we can save that energy. So it was our first observation, and we modify the steps accordingly. Then we try to make we try to see that how much maximum amount of this fertilizer we can load into that matrix, and we keep on increasing, and we can see that DAP at max we can give 10% weight by weight, SSP 20%, where RP is 10% weight by weight. And when we are adding in higher quantity, we have seen there is slowing of the polymerization, probably it hinders that polymerization process, and then some sticky consistency of the product, we cannot take it out easily, so maybe it will create problems. So this observation lead us to confine our work to 10%, 20% and 10% of these three fertilizer sources. Then also we studied the release pattern of this in the soil, and we found that simultaneous application of DAP with a low molecular acid give better concentration. Same way we also study the release pattern with other variants like with SSP, and we found the power form of release, and also we see that the low molecular acid has the initial release. Same way we also study the pattern of the product with RP, and we also see that power form of release curve. And same materials are also tested against the release in soil, and we found that the variant with tartaric acid with the fertilizer give better release in the soil. Now we come to the instrumental characterization. First we did X-ray diffractogram analysis, and you can see there is a hump in the just starting of the X-ray peak. So that hump that suggests that there is a increase in the interlayer distance due to the nanoclay intercalation. And we have also a peak of pure kaolinite, and we can compare with this peak, and we observe that where there is an intercalation, because the polymer sometimes intrude into the interlayer of the kaolinite, and also sometimes the surface hydroxyl group of the kaolinite are making graft polymer. So in the main chain there is from side chain they are making, so that graft polymerization and this intercalation, these lead to decrease in the intensity of the kaolinite peak. So this was proved by our X-ray diffractogram analysis. Further we did scanning electron microscopic analysis. So same photograph we take, and then we observe the different structures there, and you can see the different structures here of the different materials. And then also we did FTIR analysis, and we could see the the wave number respected to the materials used. So same way these are the list of the different FTIR of the different NCBC variants. Then we tested in a pot, and we found that NCBC plus DAP plus TA and NCBC plus SSP plus TA, these are giving comparatively better results as compared to the other variants. Further, after the pot analysis, since this material in the lab, synthesis is a bit difficult, because we don't have that large scale synthesis methods, and because of that we use microplot to study its field effect. And then once we did, then we can see that if we use if we compare the results with no fertilizer application, no P application, then these variants with low molecular acid, particularly tartaric acid, can give 19 to 28% higher yield, while we compare with the conventional DAP, then it can go up to 8.3% yield advantage. Now these are the photographs, and also we studied the soil properties, and we can see there is a P where we are applying phosphorus, but it is depleted in other case. And pH is also slightly improved, because the pH of NCBC is, we have seen that it is a neutral pH. And then P fixation also, where we are using, because of the chelation, the P fixation is also decreased. Then we also studied the phosphorus fractionation by using modified Chang-Jackson method, and we can see that the fraction aluminum and iron phosphate fraction is readily replenishes the phosphorus pool where we are applying these type of materials. So this is the other pools, occluded P and then calcium P. Calcium P also it is very high quantity, but it doesn't change because our soil's pH was near to 5. So because of that, and then we can conclude we have two products. One is NCBC plus DAP plus T, NCBC plus SSP plus TA, which can give better yield and can reduce the fixation and can give high water absorbency. But it requires some further modification because we are using acrylic acid as an ingredient, and once we are calculating the the cost of the material, it becomes higher than compared to the conventional. So until unless we make it cost effective, it cannot go further. But there are some way, I have seen some literature, maybe by replacing some of the costly ingredients, if we find some alternate ingredient or alternate polymer system, if we can get, like we are using polyacrylate, maybe we can think of some other polymer system which is comparatively low cost. So those things can be, but our target was to establish that these things are working. So it works. So now next step is to go for the more cost effective material. Thank you very much.
Any question is there? There is no other question.
Okay, thank you.